and I'm really looking forward to discovering some more about the materials I've been using for all these years. The Royal Academy Schools, where I'm currently curator and head of schools, was founded at the same time as part of the Royal Academy, at a time when perhaps science and art were more used to going cheek by jowl, as indeed the learned societies and the Academy sharing this beautiful courtyard is evidence of that kind of hugger-mugger moment. And indeed we have a professor of chemistry and a professor of anatomy. So those days when artists and scientists rubbed up alongside each other more frequently are evident in our history. And tonight, though, I'm really pleased to introduce Professor Andrew Abbott. Andy is a professor of physical chemistry and head of department at the University of Leicester, and his research focuses on green chemistry, by which he means environmentally friendly rather than the colour. In 1999, he commercialised his research discoveries by setting up a spin-out company making ionic liquids. Andy is an avid, although according to his school reports, totally unimaginative, I'm sure that's not true, artist. His only artistic claim to fame is that his paintings hang alongside two Monet paintings. Today, this evening, he'll combine his dual passions for art and chemistry to show us how chemical change can be used to create everything from cave art to iPad drawings. Andy.
Well, thank you very much, ladies and gentlemen. It's a pleasure to be here today. Is that picking it up? Okay. It's a great pleasure to be here today, and I had to start with a confession because I never wanted to be a chemist. I wanted to be a lumberjack. No, I wanted to be an artist, and there were only two things that stopped me being an artist. The first of which was my father. And my father was a military man from the north, and he said, "Son, there's namby-pamby art, I'll not do art with me." So he was out with Dad, and then my art teacher, Mrs. Pollard, I hope she's watching, said I was totally unimaginative and lacking in skill, in the good old days when art teachers could say, or teachers could put in your report really what they meant. So why do I paint every single day? Every day I draw. When I come to all these wonderful meetings that we have here at the Royal Society of Chemistry, I've even been known to draw outside when I'm being bored with meetings in here. So this book goes everywhere with me, and I love to paint. And the reason that I love to paint is because of this painting. This painting is the only one that hangs in my cave that isn't by me. And it was painted by this man. Any art historians amongst you hopefully will not recognise this man, because this man is my grandfather. And my grandfather gave me this painting, and he also bequeathed to me when I was 5 this set of paints, and I love this set of paints. I've only ever used them once, and I checked it yesterday and they are still liquid. So my grandfather died in 1969, so 40 odd years on, they're still paints, and I could paint with them potentially. But I have a great passion for chemistry, and what I want to do tonight is to take you through the chemistry of my grandfather's paint box and have a look at how the changes in chemistry actually led to the colours that artists use today. Now, the thing about paint is that it requires a magic ingredient, and that magic ingredient is light. So if we go next door into the Royal Academy, down into the vaults down there, we won't actually see any art, and that's because the lights are off. And to have art, we need light. And light is a very strange thing because the electromagnetic spectrum is very wide, and it ranges from everything from cosmic rays and X-rays at very high energies down to low energy radio waves. And the bit that's the visible part of the spectrum is actually tiny. So this tiny bit in the middle here is the visible spectrum, and what happens, this is the only science bit, so I can wash my hands after this slide. The only science bit is that what happens is that to be coloured, something has got to have the right kind of energy levels between its normal ground state and a stable excited state so the electron can become excited. So it absorbs the light, and what we see is the light that's left, that's reflected. So if we have a look at our spectrum, if we take a material down here which is white, then any white material reflects all wavelengths of visible light. If we have something that's black, it absorbs all wavelengths of visible light. And if we have something in between, then it absorbs one or more of those colours. So if we have something that's blue, it absorbs in the red light and reflects the blue and green. And so we'll be very familiar with a colour wheel over here. So if something appears to be red, for example, then what it does is absorbs the green part of the spectrum. Now, the problem with developing dyes is that there are two types of pigment. The first of which has an absorbance band, and what that does is absorbs just over a small region of the spectrum. So if we absorb in the yellow, what we will do, our material will appear to be purple. And the other type of material is one that has an absorbance edge, and what that means is it absorbs all wavelengths up to a certain value. So if we absorb all wavelengths up to the yellow, then our material appears to be red. And one of the issues is that many pigments that we have tend to be these band-based absorption, or these edge-based absorptions. And so what tends to happen is it's quite easy to get the reds and yellows, but the elusive colour for all chemists used to be blue. Blue was a colour which was very, very difficult to get hold of. And I'll explain a little bit later why that is. Right, so what we're going to do today is to have a look at where those colours come from. And they come from two sources. Either it's a carbon-based material, an organic material, so a natural material, or it's something that comes from minerals, it's an inorganic material, and those tend to be mostly metal-based colours. So these are the sort of spectra of colours that we see. And what we're going to do is see where that comes from. And I don't know how many of you are chemists. A quick show of the hands of chemists. A smattering of you. Actually, I don't need to explain too much. I'll go through it anyway. Right. Chemists are lazy people. There's no disagreement there. So chemists are lazy people, and they don't like to draw out full structures. So what they tend to do is they create these works of art. And I've always thought that chemistry and art go hand in hand, because I think these are beautiful shapes of molecules. And all these materials which are coloured contain one thing. And what that is where you see a line, what that does is it joins together two carbon atoms, and on those two carbon atoms there's usually another two hydrogens. So what we have here is a series of carbon-based materials, and where those carbons share 2 electrons, we've got a single line, and where they share 4 electrons, we've got a double line. And what I want you to look out for today, the non-chemists, is this alternating structure, single bond, double bond, single bond, double bond, single bond, etc. It's a bit like playing hopscotch, okay? So it's one leg, 2 legs, 1 leg, 2 leg. And wherever you see that, that's called conjugation. That's our first new word for tonight. Conjugation, and conjugation leads to coloured material. So you'll recognise some of these colours. Over there is chlorophyll, which has got a magnesium centre to it. Over here is heme, which has got an iron centre to it, which is red. It's one of the reasons that your blood is red. We've got anthocyanines, which give a range of colours, particularly in blue and yellow flowers. And we've got these carotenoids, which give us the sort of reds of our spectrum. So these are very much our organic materials. And what we're going to do is have a see where this colour comes from. And we're going to do our first piece of magic. Now, what I have over here is a plain piece of watercolour paper. And we can see that that watercolour paper is completely blank. So is this art? Anybody agrees this is art? No, it's not art, okay? But if we spray some carbonate on there, we can see quite clearly this is very clearly art, okay? So there's my first piece of art. Is it too late to go for the summer exhibition this year?
Yeah,
missed it. Damn it, next year. Okay, I'll do that again for next year. Right. So what we've done in that experiment is the classic magicking experiment. This is phenolphthalein. It's a pH indicator. It tells if we've got acid or base. And in more acidic solution, what happens is that we have this form of the molecule, and we can see the carbon there in the middle it doesn't have any double bonds associated with it, so it's colourless. And as soon as we spray a basic material, an alkaline material onto it, then we break one of those bonds and we make hopscotch around our molecule, and suddenly it turns pink. Okay? Now, what I want you to notice also, I apologise to any artists. How many artists do we have in the room? Oh, a couple of you. Okay, we've got a couple of artists. I'm not an artist. I told you I was awful. I wanted to demonstrate this, and I couldn't think of another way to do it other than a 5-minute sketch myself. So this is 2 5-minute sketches that I did late at night. And what we've got here is 2 paintings of the same thing. It's a cast in Wales. You can tell I was on holiday last week. And the top one looks a bit washed out on the slide, but you can see actually it looks more realistic than the bottom one. And the top one doesn't actually have a green paint in it. It uses cadmium yellow, cadmium red, and ultramarine, which are my 3 classic colours that I always paint with. And the one at the bottom has got my full spectrum of colours that came out of my watercolour paint pot. And you can see that actually it doesn't quite look realistic. It's a little bit too vivid. And that's because nature uses a very limited palette. So if we have a look at what trees contain, trees only contain chlorophyll A, chlorophyll B, and some carotenoids. Okay, so it's a limited palette. So if you have a limited palette and block out certain parts of the spectrum, then you'll achieve colours which look more realistic. So painting lesson number 1. So in terms of my second source of colours, which is metal-based colours, if we go to a metal complex, and this is the greatest piece of art in the world, the periodic table, then there are lots of elements which are coloured and naturally coloured, particularly in this transition block here in the middle. And what I have is a picture from my own research up here. There's a series of liquids, and I've just dissolved a series of different metal oxides into these liquids, and we can see we can get a spectrum of colours produced there. So we can change the colour by changing the metal that we have at the centre of our compound. We can also change the colour by changing what's attached to that metal. So we're going to call that thing that's attached to the metal a ligand. By changing that ligand, we can change the colour of the complex that we've got. So what we have over here is a very simple solution. This is iron 3 chloride. And iron 3 chloride, as we can see, is yellow. Okay, so there's our yellow solution. Actually, Andy, could we... Now, iron 3 chloride is yellow in water because it's got attached to it 6 water molecules. What we're now going to do is a very simple bit of chemistry, and we're going to replace those water molecules with thiocyanide. Okay, very simple experiment here. Put up against the white wall. Fantastic. Okay, now what we will see is as we add this ligand to it, we'll see very suddenly starts to become coloured, and we change the hue by adding more of this, and therefore ending up with a more intense colour. And we can get our entire spectrum by changing the strength with which that ligand interacts with, whoops, get it back on screen again, interacts with that metal. So that's a metal-based dye. And that's really the story of the initial types of dyes which we use in our artist's palette. So, thank you. What we have up here is 8 different liquids, and they're all copper 2 chloride, and all I've done is I've added a series of different ligands to them, and you can see we can get the entire spectrum from red through to blue just by putting a different ligand with that metal. So that's how we can develop different metals. What I want you to watch out for in the history of chemistry is really the development or the discovery of these transition metals here in the middle of the periodic table. Right. How many of you, like me, spend hours in the National Gallery? 1 or 2 of you. What I'm going to ask you to do, when you've got half an hour of a lunch break, they're going to phone me up and say, did you tell them all to run around here? Is not to go look at the paintings, but actually go look at the chemistry in the National Gallery. So start over in the Sainsbury's wing, walk relatively fast pace, and actually have a look, when you go from one room to the next, at the change in colours. And what you'll see is not what the artists were painting and what kind of things they were painting, but actually the colours that they were using. And as you'll see, we've got a timeline here of art from Giotto through to Hockney, and we can see a fantastic change in the colour palette that's being used by the chemist. And what I'm going to do tonight is to take you through those developments that led to the different colours which the artists were using. So what I've done now is I've done that same timeline. Rather than putting artists in there, what I've done is I've put chemical inventions in there, chemical discoveries in there, through from prehistory through to the modern day. And what I'm going to do is I'm going to break this into 6 discoveries that I think changed the direction of art each time. And so I want you to look out for these indigo-coloured boxes, and indigo is obviously a very important colour, and we'll explain that a little bit later. So what we can see is in prehistory there were a small number of elements which were known to man, and then in the Renaissance time we started to go through alchemy and discover 1 or 2 more elements, and then 1700, the golden age for art, is the golden age for chemistry. These 2 things are not dissimilar. And then we'll have a look at why the 20th century suddenly became multicoloured, and why nowadays just about anything goes in terms of chemistry and art. So those are the sort of 6 things that we're going to have a look at in our history of art and chemistry. Now, before we do, what we're going to try to think about is, what do I want my paint to look like? How has it got to behave? So here's a tube of my titanium white, which I use all the time. And what I need is I need a pure pigment. By having a pure pigment, I get an intense colour. So it has to be extremely pure. I've got to make sure that all those particles are the same size. Otherwise, some particles are going to settle out first, other ones are going to settle out later. So I've got to make sure my particle is about the same size, they're evenly distributed, they've got a transparent binder, so what sticks my particles together, my pigment together, is clear. And I need the correct flow characteristics, so it flows nicely with my brush. And I also need to make sure that it dries at the same sort of rate that I want to work through my painting. So those are the important things. And in my tube here, I don't just have white. I have my pigment, I have my binder, which glues it together, I have a solvent, which allows it to have the right transport properties, and I have that magical chemical ingredient, the additive. Okay, and the additive allows everything to behave together homogeneously in the same system. So think of those elements which are going to be within my paint, and let's have a look how we developed those elements as mankind went on. So the first great discovery that man made was clearly fire. And once he made fire, you can just imagine, obviously he's made his lump of charcoal, so now he can paint on his cave wall. And he's also found in the bottom of his fire pit, somebody stuck some rocks in there, and there's a metal. And as soon as you've got metal, then you've got all kinds of tools, you've got war can arrive because you can kill people suddenly, and now they've got trade because you want to have these metals, and suddenly the human develops into something that looks a little bit more like modern man. So carbon, the change with fire, is the first thing which occurs. And so our man is sat in his cave, and it's a little bit like the Armstrong and Miller case. What meat? Oh, mammoth. What mammoth? Mammoth, or big creature. So he takes his fire stick and he draws on his wall this mammoth, and he says, what kind of mammoth? And so he says, it has to be red. And if you have a look at those early cave paintings, mankind had a 3-colour palette. That 3-colour palette contained carbon from his fire stick, and he had iron oxide, which was red, and he had a hydrate of iron oxide, yellow ochre, which was yellow. And those were his 3 basic colours that he used. And this goes back over 40,000 years. So we've been painting on walls for 40,000 years, and I'm still painting on my walls at home. I think everybody should only have their own paintings on their own walls at home. We can all see how good we are. And have you ever noticed how that most fundamental colour, black, still pervades everybody's life? If you look around you, my pointer is black, my computer is black, my phone is black, everything is black, my suit is black, my shoes are black. And that's because a lot of what we use nowadays is in fact soot. And it's used as a filler in a wide variety of materials, and soot is still that material that you can rely upon to never fade and always be black. So it wasn't really until I started looking at this thinking, well, why is soot black? And soot is black is quite obvious really, because it's made up of graphite sheets. So graphite has these layers, and these layers have rings, and the rings have alternating single double bonds, and so they're totally conjugated, and so it absorbs all wavelengths of light. Whereas if we look at diamond, Every carbon in diamond has 4 bonds, and therefore there's no conjugation, and therefore it doesn't absorb any light, and therefore it appears to be transparent. So carbon was our first main and dominant colour. As we started to trade with other nations, what we found was that in fact there were some nice gemstones to be had. And some of these are colours which have lasted for over 2,000 years. So the first reds were mercury sulfide. The first yellows, orpiment, was arsenic sulfide. Malachite was copper carbonate. And lapis lazuli was the most treasured of colours because it was the only blue material. Now the problem that you have is when you dig up these minerals, you might have a nice mineral like this one here. We can see that part of it is coloured, but part of it is not coloured. So depending upon what ore we dig up and how we grind it, we get leads to a different intensity of the colours that we make. So as chemists, what we'd like to do is to make a really pure coloured material. So our second great discovery was made in the Egyptian times, and again it probably came from a lazy person leaving some wine in a beaker and suddenly discovering, actually my beaker's either turned green or it's turned white. And what they found was that they'd found chemicals, and these chemicals that they had were acids and bases. The most basic of chemistry that we all learn in the first lesson that we have with chemistry, acids and bases. Well, the first acids they had was vinegar, where the wine had spoilt, and they found that if they dug up their pit of ashes, then they would have caustic potash, potassium hydroxide. Again, this is a very, very useful base. So they could do chemistry, and I was going to do this very first experiment, which was to make for you lead white, which is one of the greatest whites that we can get. And I was with my colleague this morning at 8 o'clock trying to come up with these experiments, and he said, do you know how toxic lead acetate is? And I said, no, and I looked through and went, we won't do the lead experiment today. So what I'm going to do to you today is a bit of a cheat. I started this experiment just before you came in here, and I had a nice lump of zinc. You had to believe that there was a lump of zinc in here, and I put an acid in it, only not vinegar, this was hydrochloric acid. And my zinc, I thought there might be some of it left, but it's actually all dissolved. So what I'm now going to do is I've got pure zinc, hopefully chloride in here now. I'm going to do the very simple experiment, which is to add a base to it. Okay, so this is sodium hydroxide, and hopefully we're going to see a reaction between my base and my zinc salt. And hopefully, if Andy's got the camera ready, okay? Yeah, brilliant. So what we should be able to see here is, here's just simple zinc chloride in HCl. I'm going to add to it now some base, and hopefully what we can see in there almost immediately is a white precipitate that very clearly forms. Now this white precipitate is very, very important, because in history you might sort of say, well, white's boring, I don't like white. But white is one of the most important colours to the artists, and it's one of the most difficult to attain, because the slightest amount of a pollutant within that and you end up with mucky brown. Okay? So white is a very, very important experiment. And the only reason that our artist didn't initially go for zinc as the first white was because he didn't know that zinc existed. The first metal that he had was lead, and so he couldn't make anything else other than lead white. Now, lead white is a beautiful colour. It's far better than any other white we have, but it is, as we'll see later, a very, very toxic material. So, our ancient Egyptian palette has now expanded from 3 colours into 6 colours. The Egyptians painted with hematite, which is red ochre, malachite, which he made by taking his copper pot, dissolving copper in vinegar, and then making the carbonate. Then ground up lapis lazuli to make blue. Orpiment, arsenic sulfide, was still is yellow. Lead white, we've now got a fantastic white which we can use, and you're still using carbon black. So this is our basic Egyptian palette, and you can go around the British Museum and see those are the 6 colours which typify Egyptian art. Now, the Romans and the Greeks also got involved in this, and they found that actually if you could purify lead and you could roast it, then you could get lead oxide, and you get this wonderful sort of orangey red up there. And that's still used. It's actually an anti-corrosion, it's a very good anti-corrosion paint, and it's still used even though it's exceedingly toxic. They also made vermilion by heating mercury with sulfur. They could purify those two. You can dig out pure sulfur, and they found a way of making pure mercury. They also found that they could then get hold of naturally occurring dyes, and their favourite one was Tyrian purple. And Tyrian purple is taken from a small sac of a sea snail, and it takes about 10,000 sea snails to make 1 gram of this colorant. And that's why it was the most holy of holy colours, and it was only used to dye the emperor's toga. It's a very, very important colour because it was very difficult to get hold of. Now, when I was putting this together, my wife is also a chemist, so said, well, you've got to talk about the surfaces that people actually painted on. Otherwise, how do people know what chemistry went into that? And everybody always ignores the surface, but actually the chemistry of the surface is just as important as the chemistry of the paint. And to start with, people wanted to paint on walls, and so they wanted to paint on a nice white wall. But of course, the cave wall was not particularly white, and so they needed something to paint onto. And they had to develop then ways of making walls white. They also firstly put together books which were made out of parchment, so they had to make animal hides into something that looked a little bit flexible. And what they did was they took the animal hide, because you can't just write on the dog, you have to remove all the fur first, and again they took their bases and removed the fur from the skin and made an untanned parchment. And also they were painting onto things like wood, but to make wood so that it looks white, we needed gesso, and gesso is a classic primer. And what that is gesso is the a word for calcium sulfate, and they mix that with animal glue, and you've got animal glue by taking your base and boiling up a bunny rabbit for a couple of days, and you ended up with animal glue. And then once you've made your pigment, what you needed to is a way of sticking it together. Well, the caveman used to use resin and spit, and what the Egyptians found was they could use animal glue, beeswax, resin, and even egg yolk. Now, the fresco had to be painted fresh on a wall, otherwise it didn't stick to the wall. So what they did was they took calcium carbonate, they heated the calcium carbonate to make calcium oxide, then reacted calcium oxide with water to make slate lime, and that slate lime was very, very basic. When you slap that onto a wall, then you can make a kind of concrete, but the problem is that your colorant has got to be stable in pH 14, so it's got to be stable to very, very strong bases. And there are only a small number of pigments which could actually take that kind of alkaline condition. And so what people used to do was they used to paint in fresco, but then the rich colours they would paint on top of it in something called secco, and the dry layer, which would be egg on top of this wall. And so we have the Last Supper here, which is a very famous painting, which has all crumbled away because the painting wasn't done in fresco, and that the dried layers on top of it actually peeled away with time. Now, the most common binder that people used to use was egg yolk, tempera. And I had a fantastic epiphany this morning. 8 o'clock this morning I was stood with one of my colleagues, and I said, I'm going to do this as a demonstration. I'm going to make some tempera for them, and I'm going to paint this on and show them how easy it is. I'd never done it before. And I did it this morning, and it's absolutely horrendous. What I wanted to show you is that what I did here was I took zinc oxide, and I ground it up with egg yolk this morning, and it still smells eggy. And then on the other side, I took my lovely titanium white over here and painted the two. And what you can see is that zinc oxide is a beautiful white, but actually, I'm going to pass it round for the people at the back, you can see that this is actually very, very yellow, even under these lights. And so the whites of classical art are in fact quite yellow because they contain carotenoids. There you go, it's one of my artworks, I'll sign it for you later. They contain the yellows of egg yolk, it's the carotenoids, and you can see quite clearly the classical whites have got a yellow tinge to them. So the binder, the clarity of the binder is very, very important. So, if we look at European history, we start the first millennium AD and we call them the Dark Ages. And very little is known about the chemistry. There's probably as much myth as there is as truth in the chemistry of the Dark Ages. But this is the time when chemistry started to come together. Because if I was to make you, go back 3,000 years and sit in our cave and sort of say, here's some material, all I can use is the materials around me, why would I ever think, actually, I can take that material and I can break it down into its fundamental building blocks? Nobody would ever guess that this tablecloth was made up of various building blocks. And yet, what people started to find was actually, as they started to experiment with matter, it could be broken down and broken down and broken down. And all these myths about the elixir of life and the philosopher's stone, really what happened in the Dark Ages was people were trying to experiment to say, how can I break things down to see what they're made of? And what happened in the Dark Ages is probably more important than anything else to our story, because what we decided to do was to purify natural materials. And we developed those classics of the chemist, the distillation, filtration, recrystallization. All of these techniques came about, and the artists pretty soon cottoned onto the idea, let's make that material pure. So that's what happened in the Dark Ages. As you walk very quickly out of the Sainsbury's wing, what you'll find is that you go from all these really flat tempera pictures, always of something like the Annunciation or something biblical, into this really bright room, the Dutch painters, the Dutch school. And suddenly we come to the Renaissance, and if it's me, I don't like anything before 1800, but suddenly I came to this room, I was explaining to my son, how the history of art, I came to this room and you go, whoa, what happened to the colours in here? And suddenly the colours become really, really bright. And they become bright because now we've gone away from using this tempera, and we've discovered that if we use oils to act as the hardening agent, what we can do is we can make a material that is very, very transparent. And the beauty of it is it doesn't dry immediately. So that egg tempera there, I really messed up a pair of paintbrushes this morning. I hadn't realised it takes about 2 minutes for this stuff to dry. So you can imagine some of these fantastic works. So go back to the Sainsbury's wing, go back to those sort of pre-Renaissance pictures, and just sit there and marvel at the artistry of those people, because you couldn't put one wet colour onto another wet colour. You couldn't blend your colours into them wet like you would nowadays do. They had to be done really, really quickly. And to get any kind of detail onto those surfaces was very, very difficult, because if you make it too thick, it'll crack and it will flake away. So tempera paintings, I have a whole new respect for them as from 8 o'clock this morning. And we've used these oils for many years. You all actually look about the same era as me. So you can remember sticking windows in with putty. That putty was linseed putty, and you had to wait for that putty to set, which it did by reacting with oxygen in the air, and to give you a hard putty. And you all look as if you can remember linoleum as well. Linoleum comes from the word linseed oil, and oleum, which is oil. And we used to dip rags into linseed oil and oxidize that, and that gave us a really hard, rigid material. So linseed oil has been used for many years. They also use things like walnut oil and poppy seed oil as well. But this big change came around mostly in the Dutch school. Van Eyck was one of the main people who popularized this as a technique. And if you actually go and have a look at this painting, the betrothal of the Arnolfini, again, it might be your taste, it might not be your taste, but go and have a look at it and compare it to the paintings which you had a walk through about a minute previously. The detail on it is absolutely phenomenal. And also what you see that really, really shines out is the white. The lead white that comes out of that picture really bites you when you have a look at it. So we've seen that the purification of oils, the ability to purify pigments, is now leading to really bright colours. And we can see that in the dress of the wife here over here. And these two paintings we can see are around about the same time. Very, very different feel. The one over here looks flat, the one over here really three-dimensional. So the chemist has changed the way in which the painter was now able to paint. He could paint wet on wet. It might take several weeks now for the painting to dry, and so you could blend in colours, and that's where the depth of these paintings actually comes from. In the Renaissance, we started to discover our first new elements, and things like antimony up there went into Naples yellow, and we start to see the yellows which were coming out and sort of work like Dura. And as we started to travel, we discovered the Americans. We found, oh, those Aztecs, they're doing some very interesting things. They're taking beetles, they're collecting beetles off cacti, they're crushing them up, and they're making a red dye. And what we found is that if we mix this with potash alum, then we could make a material which was a bright red colour. So that's where our cochineal lake came from. This is the carotenoid, the material that goes into making that red. So, the great discovery, the great period for chemists, round about 1700 to 1800. What happens in that time is pre-1790, we've got about 29 elements or 29 materials which are known to the chemist. In the 50 or 60 years that come after that, we almost double the number of elements that we know. Okay? So the chemist has found ways of breaking down new materials into new compounds or new elements, and therefore then reacting those to see, first of all, does it react with oxygen? Does it react with sulfur, which are our classic two alchemy experiments? And we found these brilliant new colours. Now, what everyone had been looking for, because the only way in which we could possibly get blue was by taking lapis lazuli. And when you put together your request for a painting, what you did was you wrote one contract to say, I would like you to paint this picture, and you put another contract in there to say, I would like you to use this much lapis lazuli, because lapis lazuli was really, really expensive. And so it was saved for the most important colour that they could find, and that's one of the reasons that, in fact, it's the only reason, that the Madonna's veil is always blue, is because people wanted to show how rich they were, how much lapis lazuli they could actually use. Now, as I said, it was a very difficult material to get, and as usual, it required a lazy chemist and one who didn't purify his material. So what I'm going to do now is make our final colour, and what we have here is, again, we've got iron chloride, and again, what we can see is that with our iron chloride, we've got a yellow coloration, and I've also got over here some potassium ferricyanide, which again you can see is nice and yellow. And if the artists of the 1600s could see the following experiments, they would go, oh my goodness, is it that easy? So up here we have a nice yellow solution, and what we're going to do is just drop into there a couple of drops. And we can start to see immediately that goes a lightish green and then a more intense blue. And the more we add, so that's at the moment is a dye, so it's soluble. If I add some more to that, by the end of this lecture, that will have settled out and given us a brilliant blue. So I've now got an insoluble complex. And that blue is due to the fact that I've got an iron 2 centre, an iron 3 centre next to each other, and we get a charge transfer. And almost all the blues are blue because of that charge transfer which occurs. What I'd like you to notice here is the hunger for blue. We can see that Diesbach in 1704 in Berlin discovered this. And 5 years later, it was used in its first painting, Van der Werf. We can see this painting here must have caused so much consternation because suddenly this blue is there, it's used in huge amounts, and it stands out like a sore thumb from all the other colours which are around it. So we finally got a blue. Then came arsenic. Fantastic. What we found was actually we could make some fantastic colours, complexes between copper oxide and arsenic oxide, and what we found was this beautiful green, and this green really characterises Victorian art. So everyone loved this art, this green colour, which was called Sheiller's green, and they used to include it in everything. All of the wallpapers, if you go around these classical houses, have got green wallpaper. The problem is that copper arsenate is one of the most toxic compounds you can possibly find, and it was very good at decomposing to give you trimethyl arsenine, which is exceedingly toxic. And it's been associated with the deaths of many people, including Napoleon. But it's actually still used today. If you ever look outside in your garden, you've got that lovely new fence which the wife has made you put up. It's green, and it's green because it's actually dyed with something that looks very much like this, which is a copper arsenate. And we're still using it because if you think about it, you want that fence to last for a long time, and absolutely nothing survives copper arsenate. So it's a fantastic wood preserver. So, in our golden age, 1700, we discover the 3 C's. The first of which is cobalt, and you can see that very rapidly after discovering it, we've got a series of colours which come through: cobalt green, cobalt blue, cobalt yellow, cobalt violet, and cerulean blue. Fantastic new, vibrant colours which the artist latches onto pretty quickly. And I'm going to show you something from my research now to show you how cobalt changes colour. So this is cobalt chloride, hexahydrate, so again that's got 6 waters on it. This is how we make ionic liquids, but that's as a side. Here, what I've done now is I've added a chloride ion to it, and I've made a liquid by mixing together 2 solids. And that liquid, that's not speeded up, that's in real time, it's not heated. It takes about 10 seconds, and again I've got a beautiful blue. So cobalt is classic for these beautiful blues. And the second of our C's is cadmium. 1817, we discovered these beautiful yellows, oranges, and reds. But in fact, cadmium didn't become a useful colour until about the sort of mid-1800s, was because we couldn't find any ores. It wasn't until we discovered cadmium ores in North America in large quantities that in fact this became a very useful and very popular pigment. And have a look around in the late 1800s, everything bright yellow, bright red. The third of our C's is chromium, and we can see chromium gives us these fantastic vivid greens, yellows, and when we mix them with elements like strontium and lead. The chemists amongst you are going to go, yeah, that's why artists used to die very quickly, was because the pigments that we're using are exceedingly toxic. But possibly the greatest discovery that changed all of art was none of these colours whatsoever, but it was, in fact, my humble tube. The artist previously used to have an army of people who would make his pigments for him. They had to be made fresh, and they had to be ground and mixed with the oils and used typically in the studio. What happened in 1840 was somebody came up with a brilliant idea: why don't I use this new metal tin and actually put them together in a tube? And so the tube was born. And suddenly, as soon as you had the tube, artists could go in the field, artists could paint new things that they saw, artists had new lights, new pigments, and the whole of art changed. Because the price of pigments came down because they could be mass-produced, and suddenly the amateur like me could go out and paint. Brilliant. Art for the novice. No. The great problem that we had was actually one of chemistry. Because to put it in a tube, you need different flow characteristics to if you'd make them in the studio. And what they needed was they needed solvents, they needed our pigment to be compatible with our transport agents, and the problem that they had was this just didn't work for some pigments. And so what they found was that some pigments were great in tubes, and other pigments were absolutely lousy, and typically it was the browns which didn't tend to flow. And so what we find is from about the 1850s, browns were used less and less as people decided to go to these pre-prepared tubes. And we can see that in our eponymous hero from this talk, in the work of Turner. And we can see that from going from 1800, where he's typically using browns, up to the age where we've got these cobalt blues which are coming in, and suddenly our same scene, Battle of Trafalgar 1806, Battle of Trafalgar 1824, whoa, we've got blue. And suddenly these cobalt blues come into it. And then we've got this picture from 1840, which was described by Ruskin as one of the greatest paintings of water ever. And you can see I got here early because I bought a book on Turner and the book in here. And I've been reading for the last hour actually about people who describe Turner's work as revolutionary, because if you have a look at what he did, he got across the mood with the colour more than any other artist who had gone before him. He embraced the new colours, and he had this thing with Mr. Windsor of Windsor and Newton, where they got the latest colours that he could, And he was the exact opposite to me, so he was a good artist who dabbled in chemistry. And what he found was actually he could take some of these pigments and try it. He experimented for himself, which is why it's a sort of preserver's nightmare. He experimented making his own pigments and making his own binders. And so that's why the work of Turner is revolutionary. And what we see as we go into that sort of everyone's favourite period, the sort of Impressionists, why it's everyone's favourite period is suddenly we go into the light. And we can see, because of that problem associated with these brown pigments, this is a painting from Renoir, and we can see the palette that Renoir's used over here. Orange, yellow, yellow, green, blue. There's not a mucky brown in sight. Okay? So suddenly, what happens is that these people are painting, obviously, out in the fields, and they're using these brand new bright colours because it's new, it's funky, it's not the horrible brown colours they used to. So we've changed their palettes. And what we can see here is 3 pictures painted with 3 different palettes. We've got our classical palette over there, using the sort of umbers and ochres that we first discovered. Now we've got our Impressionist palette, and what we can see over here is our modern pigment palette, which is due to organic pigments. Same scene, different pigments. At the top there, different colour wheels. So you can see that really what's happened is the chemist has been instrumental in changing the materials that our painters are using. Now, I said it's a chemist's nightmare. Most of these materials are exceedingly toxic, and luckily many of you will now know that most of these materials have been replaced. But if we look through it, we've got lead, chromates, cadmium, cobalt, arsenic. It's a who's who of don't go near it. Okay? So many of the artists are thought to have either suffered with their health or gone mad. Caravaggio is known to have had lead poisoning. Van Gogh and Goya suffered tremendously from using arsenic in a paint. And so what's happened is lead is one of the main contributors to this. This has been replaced with probably inferior whites of titanium and zinc. But what stopped these materials coming through was not that they hadn't been discovered. We've known titanium oxide for many years, but because titanium oxide always has iron associated with it, so to purify it to get this brilliant white is really, really difficult. So, discovery, our penultimate discovery, discovery number 5, is really the change in modern chemistry. So we've gone out of that inorganic chemistry now into the synthetic organic chemistry, and this again is discovered by accident. Mid-1800, 1850, William Perkin, one of the gods of chemistry, discovered, quite by chance, he was trying to find a way to get to quinine, so to get to an anti-malarial, and he found that actually he'd boiled up this material, and as with all experiments from undergraduates, it had turned black. But he found that washing it out with alcohol made it turn purple, and he went, oh, there's a new colour. And he washed out this material, and it had this colour indigo. And this is the President's Medal from the Royal Society of Chemistry. This is what God wears around his neck. And this ribbon from God's medal is actually dyed with the initial sample that Perkin made in his laboratory. So Movine was the first synthetic organic dye. Now, what we very soon discovered through mostly German, English and French chemists was that actually you could purify organic chemicals into very, very simple building blocks. And one of the biggest, most important, is that of aniline. And it's why companies like BASF, Badische Aniline and Soda Fabrik became very famous. So Bayer, again, was a great German chemical company that grew because of the colours that it made. And it found that if it took aniline, it reacted them to make this diazo compound. It could then couple them to make a variety of diazo compounds. And to the non-chemists amongst you, that will mean nothing. What I'm going to do is I'm going to show you some pretty pictures. And these are some dyes. And what I want you to notice, what I've circled in red, is that diazo link. And pretty much you can join any building block with any other building block, as long as it's got a diazo compound in between it, and it'll be coloured. So, of course, this is the chemist's paradise. You can make whatever colour you like. From that basic click chemistry, you can go from red, through yellow, through blue, through green, and even to black. And what it means is that you're not reliant on these really heavy metals which are very, very toxic. And the only problem with these azo compounds, they're very, very nice. You can get a wide spectrum of colours. The only problem with them is they're not particularly stable to ultraviolet. So in the 1930s, we found again, totally by accident, these compounds here which are called phthalocyanines. These have a nice ring structure that you can see at the top there. And that ring structure looks like something we've seen before, heme and chlorophyll, which is what nature makes. It makes these ring structures and then complexes them with a metal. And there came these really vivid iridescent blues, which were phthalo blues. So by complexing with cobalt, nickel and copper, you can make phthalo green and phthalo blue, which is every artist's favourite bright colours. So again, quite by accident. Now, this is now getting into my lifetime, and I thought to myself, how am I going to sort of finish up talking about modern chemistry? And it's exactly the same as saying to you, how would you sum up modern art? Oh, it's just too vast. And exactly the same is true for modern chemistry. It's just too vast. You can have any colour of the rainbow that you want, simply by looking at how nature puts together these conjugated systems and these aromatic systems, and when you bolt them together, you can make just about any colour that you want to. So much so that companies actually design a colour. So you don't need to see the word JCB to know that that's JCB yellow, or this green over here. These companies have patented their own colour. They own that colour. And they've made it by making a wide variety of these conjugated organic structures. And they're relatively simple to make, and what's driven all of this is in fact not being the artist, but the car manufacturer. And it's anybody who bought a Ford in the 1980s, you bought a Ford Red, it's a classic Ford Red, you parked it on the drive, and when you came to sell it, it was Ford Pink. And what people were trying to do was develop more and more light-stable compounds, and that's where these colours have come from. We then enter our final great discovery, which is the discovery of the plastic age. 1930s, 1940s, everybody needs a war for a reason. One of the things that came out of it was synthetic acrylic polymers, and this is what led to the acrylic binders. And acrylic binders now have no conjugation in them, therefore they're totally clear. So what binds together my acrylic over here is the same material that you have in Perspex. And what happens is that when we bind it, we've got a binder which doesn't have any colour whatsoever. It's flexible, it's durable, it lasts for ages, it even filters out ultraviolet light, and so it makes my pigment much more light stable. So we've got people up here like Liechtenstein who use these, cottoned onto these acrylics really, really quickly, and you can see that. You look at pop art, you've got these really, really vivid colours which come out. So, less likely to crack. Now, anything goes. You can have fluorescent paintings, you can have chemiluminescent paintings. There's a photograph taken with a glow stick. We can have radioluminescent paintings. Just about anything goes. And it's the chemist that's making the dyes which become excited within these complexes, which are very, very important. Now, had my lecture been brought last week, then we could have all marvelled at the Hockney exhibition, and Hockney has now taken, we've seen so much press recently about his using new media, so gone are the canvases, gone are the acrylics even in some cases, and he's embracing new media and electronic media, because now art is not something you hang on the wall, it's something you have on your iPod. And so what we now need to do is develop materials which can be used for portable displays. Who'd have thought 40 years ago, when I was a kid starting in chemistry, who'd have thought I could pull out my iPod and show you a picture on my iPod? Horrendous to think what we've done. And it's due to the chemist's discovery of light-emitting materials. So we take that same aniline, which is used in colours, and we polymerize that, we make polyaniline, and that can be used in our light-emitting diodes, which are in our screens for our iPads. So nowadays, the infinite palette is there, and you can get just about any colour you want to. My wife is threatening to buy me an iPad, and I said don't, because I'll never do anything else. So that's the reason I can't show you on an iPad. I'm itching to get one. So the chemist has been instrumental in getting us just about every single new material that we use in our lives. So, to draw this thing together, what we've seen is that chemical discoveries have changed the direction of art. They've changed the colours that the artist now uses. And the question that you've got is what comes next? And the answer is, I haven't a clue. There's bound to be, it's not going to stop with the iPad. What's next is really, really exciting. And even if you're not a chemist, even if you're feeling a little bit down with all the news that's in the news at the moment, I just have to sort of finish by thanking Giro Frisch, who did all the experiments for me this morning. And if any of you are sort of interested in this, it's a fantastic site, windsorandnewton.com, has the history of all the pigments on it, and there's a lovely thing, web exhibits, which has even got some of the chemistry also in it. If you're feeling depressed, I leave you with a quote, which is that art washes away from the soul the dust of everyday life. So just go and do that power walk round the National Gallery, but I didn't tell you to do it. And finally, if you are inspired to paint, and even if you have no talent whatsoever, just like me, I'll leave you with one word, and that word is experiment. Thank you very much.
Thank you very much, Andy. That was a really fascinating skip through the National Gallery and race through the colours, all the colours of the age. Really, really interesting. And I suppose we have now time for some questions from the audience. Perhaps I could be allowed to chip in with the first one, which is maybe to ask if who's driving the invention. I wonder if it's the chemist in search of a kind of commercial uses of new colours, or if they're the byproduct of things that are to do with commerce, which then benefit the artist as a secondary thing, or whether the artists are...
I'm fairly certain it's not the artist, because I think if you still go around my art shop, the colours are very, very similar. I think what's changing, I think, is the consumer product. So I think it's things like, the colours that we have on our walls. And every single year, when Mrs. Abbott says, I want a new colour in the living room, that colour changes every single year. So I think it's fashion that's dictating a lot of these colours and opening up new palettes. And I think that's then having a sort of change into the artist palette. But I think the big changes which are coming in the artist palette are really the new media, so the fluorescent colours, which I think are coming out. But I think the artist is also benefiting from, I don't have to use cadmium sulfide in my cadmium red. My cadmium red is cadmium red hue, so it's one of these azo dyes which colours my paint. So I'm winning out there from not dying from painting. But I think that it's fashion that's really driving colours. So it's consumer market. It's my opinion, I don't know.
Anybody who has any questions, there is a couple of mics. If you could wait for the mic to reach you, and maybe once it has, if you could stand and give us your name as well before you ask.
I've stunned them. It's fine. I think there's a mic coming up.
You mentioned how nowadays manufacturers make all sorts of colours, and colours have been invented to go on the artist palette. But what doesn't seem to have attracted the attention of manufacturers are the properties of the colours when they've got to the palette. When you mentioned early on a drying time, but there are other properties, especially, for example, whether a paint is opaque or transparent, that influence the course of art, absolutely totally, and yet manufacturers don't seem to be bothered about that at all. Can you perhaps comment on that?
It's a very, very involved area, because obviously just about everything that you put into the artist palette is going to change the basic colour, the hue of the material. It'll change the amount of light which is reflected. By changing the particle size, you change the reflectivity of it. What often happens is the additives that you put into actually, most of the pigments, the inorganic pigments that you use, are obviously very good at binding with water miscible liquids. and the organic dyes are better for oil-based systems or acrylic-based systems. And therefore, you've got to put stabilizers in if you've got an inorganic pigment that you want to put into a water-based system. And a lot of the times, those are sort of emulsifiers, a sort of surfactant, so they look like soap molecules. And what those do is they change the surface properties, and by changing the surface properties, you change the way in which light interacts with them. And so a lot of times, it's actually a compromise of the binder that you use and the pigment that you use, and actually the emulsifier, which actually changes the colour properties of those materials. So I think it's a big area that sometimes you don't have many choices in. But I know that people are developing new ways of binding pigments to binders, and it's that sort of interface which is very, very important. Good question.
Thanks. Joyce Townsend, Tate Britain. Artists at one time were quite key consumers of colours, particularly in an era before photography.
Mm-hmm.
And even up to the middle of the 19th century, you can see that they were using expensive, exotic materials. They were almost creating a market and an environment where it was worthwhile to produce them.
Mm-hmm. Yeah.
Today, it's completely consumer-driven market. Artists are a tiny proportion. They probably did play a part.
I think that's right, yes. I think that there were relationships between the pigment producer and the artist, where obviously you had a much smaller community of artists, and your pigment producer probably knew all of the artists who were local to them, and probably developed pigments for them. So I think mixing of pigments, grinding of pigments was very common. So I think you're right. And I think, Turner especially had an interaction with Winsor, and I think Winsor actually gave him suggestions as to the colours that he was using, and Turner, I think, wrote back and said, actually, I'm the one who dictates what colours I use.
Yes, he did, and he had relationships with other manufacturers throughout his life, and there are even Turner's notes, as though from a chemistry lecture such as this, where probably he was listening to someone talking about the manufacture of the early industrial products.
Yeah. Thank you.
Okay. If you go around some of the exhibitions in country houses these days, you're going around in virtual darkness.
That's right.
Because they're extremely worried about, well, they say fading. I'm not sure whether it's fading, a yellowing of the linseed oil type of binders, but if in a couple of 100 years' time I was to go round an exhibition of today's paintings, could they be viewed in reasonable sunlight? And if not yet, when do you reckon that will have occurred?
I think one of the issues that you have is that a lot of the pigments have actually been launched very quickly, and I think it is, I'm no expert in this area, but I think it's one of the issues that people have about conserving modern art, is that people were using new kinds of pigments which weren't light stable, so they were just sort of saying, I want to use that colour because it's available now. So some of the sort of Hansa yellows particularly, where they were saying, well, actually, I just want to use that. And so probably those pictures are very, very difficult to conserve, and we might find in 50 years' time those are almost transparent. And we find that, if we look at some of the colours from the mid-1800s, where they were adopting the colours very, very quickly before we knew the properties of them, they're very, very difficult to conserve, and a lot of the chemistry that they used then has actually been shown to, the paints have either flaked away or disintegrated. So the answer to that is probably within the next 50 years, I would have thought that the colour chemists can develop really light, stable colours. But will the art be worth preserving? I don't know.
There's a question right at the back.
I wanted to ask about the colours that have been discontinued toxicity.
Mm-hmm.
Have all of those colours been replaced by new synthetic forms, or have they just been abandoned as possible colours to use? I think of lead white, for instance. I mean, there's no modern white that's much like it.
That's right.
Anyway.
Yeah, I think there's some classic colours. Orpiment, for example, is such a brilliant vivid green, vivid green, that it's very difficult to replace. White is the classic one. I mean, you've seen from the piece of paper that went round. Titanium white is a lovely white, but you compare it to lead white, and it's like chalk and cheese. So white is a very, very important case. I think most of the cadmiums have got hues now, which are roughly the same colour. But again, you could, depending upon how the cadmium was made, because cadmium sulfide and cadmium selenide, it was mixtures of the two. You've got different hues in each of those, so it's actually attaining the same colour each time was very difficult, even with the inorganic pigments. But most of those classic colours, the ultramarines, have been replaced with synthetic colours now. Yes.
Thank you.
My name's Helen Matheson, and I'm just wondering, you've been talking about the toxicity of the earlier colours.
Mm-hmm.
What about all these amazing things they're making now? Could there be an environmental problem in the future with those?
With some of them, they are toxic, not obviously as toxic as the heavy metals. And I think that what the bigger issue is not necessarily the artist palette, but it's the consumer palette. So, for example, colours like red lead, you can still go back down to B&Q and buy red lead. It's unsurpassed in terms of its anti-corrosion properties, and that's used in such large volumes that it's very difficult to compare what the artist uses and what the consumer uses. So they're trying to get rid of some of those colours, but things like cadmium yellow and cadmium red, there's nothing in terms of the light fastness like them, and so that's why many people who use them, they're still used in some car colours, and people are trying to get away from cadmium, and it's those large-scale uses, particularly where they're sprayed, that there are environmental issues. But yeah, there is an environmental issue with those kinds of paints, but I don't think the artist palette is used in the same sorts of volumes.
Andy, I think we've come to the end of the questions, so I'd just like to say thank you very much on behalf of all of us for a really fascinating evening. Thank you very much.
Thank you.
You're welcome.
Welcome.
Fantastic talk.